We've seen how to take first derivatives of parametric equations. What about second derivatives? So I have a parametric equation. X is a function of t, y is a function of t is in some range. I'm going to start by writing down the wrong statement. So here's what is not true. The second derivative is not going to equal this analogous statement you might guess based on the formula for the first derivative. That is wrong. In this instance, the derivatives, even though they have the fraction-looking notation, do not behave as if they are fractions. So what is the correct statement? Well, if you want to, here's the true statement. If you want to take a derivative twice, you begin by taking the derivative once. So I need to take the derivative of the derivative. That's how you take a second derivative. I already know how to take the derivative of a parametric equation. You do this. It's the derivative of y with respect to t over dx dt. But in this case, your function y is the derivative already. So this is the true way to take a second derivative of a parametric equation. Let's see an example. What if I have x is e to the negative t plus 1 and y is equal to e to the t, and t could be any value? Well, the first derivative, let's take that to begin with. So the first derivative, dy dx, is dy dt over dx dt. So in this case, dy dt, the derivative of y with respect to t, is simply e to the t. dx dt is negative e to the negative t. So if you simplify a bit, I think you get negative e to the 2t power. So that's my first derivative. Now for the second derivative. So the second derivative, I take the derivative of my first derivative. And the strange thing at first is that you also divide by an extra dx dt, an extra dx dt. So I'm going to divide by another dx dt here. So what do I find? Well, the derivative of negative e to the 2t is negative 2e to the 2t, and I divide by another negative e to the negative t. So you could simplify a bit, and I think you get 2e to the 3t. So there, that's how you take the second derivative of a parametric equation. Let's do another example. Let's find where the parametric equation x is cosine t, y is sine t. Let's say t could be in between 0 and 2 pi. Let's find where this is concave up. So I remember what the graph of this parametric equation looks like. The basic underlying shape is a circle, but we know that a parametric equation is more than just a shape. A parametric equation has a starting point, an ending point, a speed, a direction. So yes, the shape is a circle, but the parametric equation describes motion on that circle. My starting point is here at t equals 0, and I traverse the circle counterclockwise at a constant speed So I go counterclockwise at a constant speed, and I end at the place where I started when t is 2 pi. So in calculus, I remember that I could find where I have a concave up property when the second derivative is positive. So I'm going to take the second derivative of this parametric equation and figure out where it's positive. All right, here's my answer. Well, the derivative, dy dx, that's dy dt over dx dt, that is equal to cosine t. The derivative of sine is cosine. The derivative of cosine is negative sine t. So there's my derivative, dy dx. I think you can call this negative cotangent t if you'd like. Okay, what about the second derivative? So the second derivative, dy dx, is, second derivative, is the derivative of my first derivative, so the derivative of negative cotangent t with respect to t, and then I divide by another dx dt. So I remember the derivative of cotangent. If you don't remember it, it's fine. With an extra negative sign, I believe I get 1 over sine squared t. And then the derivative dx dt was negative sine t. So I believe you could simplify this and get negative 1 over sine cubed t. There, that's my second derivative. But I'm asking where my function is concave up. So I want to know where my second derivative is positive. That means to make the second derivative positive, I need sine cubed of t to actually be negative. Because when sine cubed t is negative, it'll cancel with the extra negative sign I have in front here and give me a positive number. Sine cubed t is negative exactly when sine is negative. So I actually need sine t to be negative. Now, I remember properties of sine t. Sine t is negative. This happens when t is in between, well, strictly between, pi and 2 pi. That matches my expectation based on my knowledge about the parametric equation. This is the value here on my circle as I'm going around counterclockwise. This is the value t equals pi. And I could tell that on the interval from negative pi to 2 pi, my function is concave up. Concave up, I could see that graphically. So my answer for where the second derivative is positive matches my intuition about where the function is concave up. All right, fantastic.